Hello, lab rats and junior lab rats, as well as any learn along guests that we might have with us today. This is actually our lesson 29 lab for the Rat Pack, which is our combined junior lab rats and lab rats class, which we would typically be holding on March 17th, St. Patrick's Day. But we are going to have to do this one virtually because of coronavirus. All right, so we're going to model any atom. So first things first, what's an atom? I do expect my lab rats and junior lab rats to be able to answer this question, but just in case it's a new question to some of you learn along people, or maybe you just need a refresher, an atom is the smallest component of an element. Atoms of the same or different elements can combine to form molecules. So this might bring you to ask the question, what is an element? An element is matter that cannot be broken down into other substances. Well then, so what's matter? Notice I didn't ask you what's the matter. That's a different question. So what is matter? Matter is anything that has mass and takes up space. Mass is basically how much stuff there is in a given volume, or how much stuff makes up something. So your matter is anything that's made of stuff and takes up space. So we're going to use this graphic as an example, and we're going to pretend these little green spheres here are atoms. This is not really what atoms look like, as you'll see in a minute, but just for argument's sake, we're going to simplify. So here we have 3 green atoms, and these 3 green atoms can do one of 2 things. They can either combine with like atoms, which would mean they're all of the same element. So we'll call this the green element, okay? And in this case, you've got 3 green atoms that came together and formed one molecule of green element, all right? And then the other thing they can do is combine with different elements. So in the top circle there, you have all green atoms from the same element, which have just formed a larger collection, which makes up a decent chunk of matter there. And if you look at the bottom circle, you'll notice you have a different type of atom involved, which would be from a different element. So when you have 2 elements together like that, it's called compound. But the difference is that when you put like elements together, the green square at the top is going to represent what we call a pure substance, which is just an element in its purest form. And then down here at the bottom, the blue, if you notice, is not purple or green. It's a totally different color. So that means you have a completely new substance formed by combining the atoms of 2 different elements. Now you can combine more than 2, but we just simplified as 2. All right, so then let's move on to what does an atom actually look like? Well, there's been a lot of different theories over time. We've gotten better at figuring it out. So back in 1803, we had John Dalton, and John Dalton kind of looked at atoms the way we were just modeling them, like little marbles or hard spheres. He did believe that they were the smallest particles, the smallest thing you could break down, basically. And he did recognize that all of these atoms seem to be representative of different elements. So if you had only gold, you would have only gold atoms making a gold element. And so he was correct about that. He was incorrect about atoms not being indivisible. They can be further broken down because they are made up of even smaller particles. And we found that out when we get into stuff like nuclear fission and whatnot. So let's look then at 1904, we had Thomson, and Thomson discovered that there were charges to these particles within matter, that there were small things and they had a charge, and looking at the negative charge. So the negative charge are what we now call electrons, and we call them corpuscles. So his model is called the Coulomb-Cutting model because basically he thought of it as like a big blob of positively charged, negatively charged things. Then we move on to Rutherford in 1911. So we're just a little less than 100 years ago, right? So Rutherford, he realized that there was a positive charge, but that it was localized in the very center of the atom, that it wasn't big spread out blob, kind of like Thomson thought. And he realized also that the negative particles, or the electrons, that they actually move all around the outside of the atom. But what he didn't realize is that they actually move at certain levels, or what we call shells. He kind of thought they all circled independently. Now, he's definitely right in that there are different kinds of particles, but what he didn't explain was why electrons remain in an orbit around a nucleus. So then we get to Bohr, and this is the kind of model we're going to do today because they're easiest to do in 2 dimensions. So here's Bohr, and in 1913, so again, just a little less than 100 years ago, he kind of went with Rutherford's model and then modified it a bit. And he proposed that there are stable electron orbits, and that basically what he meant is that you want every electron to be at its lowest energy level in order to keep the atom stable, and that there were certain levels or kind of spheres surrounding the nucleus of the atom that could contain a certain amount of electron energy before you had to go up to the next sphere. And so he was wrong that moving electrons should emit energy and collapse into the nucleus. So the model did not work well for heavier atoms, but it worked pretty well for, you know, your lighter atoms, your first atoms within the periodic table. And the last thing we have Schrödinger, 1926, so a little less than 100 years ago. And he came up with this kind of quantum model, which is much more accurate and very difficult to depict visually. It shows electrons don't move around the nucleus in orbits, but in clouds where their position is uncertain. And it's still widely accepted as the most accurate model of the atom. We're going to go with Bohr because, like I said, it's so much easier to model in 2D. And it gives you some idea about energy levels and energy shells. Okay, so let's move on to this part. So introduction to this lab. Here's what we're going to do. We'll be using M&M's, Skittles, Smarties, gumdrops, or other colored candies to represent subatomic particles and make a Bohr model of an atom. So here are the materials you're going to need. So you're going to need a printout of the Model Any Atom documents, which should be available with your subscription. There'll be a link for that. And if you're in the Lab Rats or Junior Lab Rats class, that's of course going to be attached to your weekly notes. Pro tip, you might want to make a few copies of page 2. It's also another great idea to laminate pages 2 and 3 and use dry erase markers. So there are, you're going to need many pieces of small candy in 3 different colors. If you don't have candy, you can use anything in 3 colors or types, like buttons, coins. You can use 3 types of coins. Paper hole punches, like out of your 3-hole puncher, just shake them out. There are different colors in there. It's just not as fun. You don't get to eat it at the end. And you're going to need a pencil, unless you've laminated, then you'll need a dry erase marker. So now's a good time to pause the video if you need time to gather your materials. So methods, here's what we're going to do. We are going to find this chart here, all right? So you're going to find this image on page 2. It's the table you're going to be filling in today. And you're going to choose an element from the periodic table, which is page 3 in your packet.
First, it's best to choose one of the first 10 elements for the purpose of modeling in this lab. You're going to copy the information from the periodic table into this table on your lab. And you're going to determine the number of protons, neutrons, and electrons that you need to model one atom of your element.
Then you're going to model. So here's how it works. Here's your table, okay? And then here is your periodic table. So for example, we are just going to go ahead and give
carbon a try. So
carbon, and we're going to have a little closer look at it. So here it is, kind of blown up. So we're going to copy the information from the periodic table into the smaller table in your lab. So we got carbon, right? We're going to put its name in, carbon. We're going to put in its atomic number, 6. That's in that top corner. And we're going to put in its atomic mass, all right? Now, we're going to determine the number of protons, neutrons, and electrons you will need to model one atom of your element. So in order to do that, you have to know that your number of protons equals your atomic number. So when you see this number here, you know that that is the number of protons you will be needing for this lab. And your electrons are going to be the same as your protons in an atom of neutral charge. So I want you to look under the words protons, neutrons, and electrons in the top of the table there on the left. So your protons have a plus sign because they have a positive charge, and your neutrons have a negative sign because they have a negative charge. Your electrons have a negative sign because they have a negative charge. Your neutrons are neutral, they have no charge at all. So if you want an atom that is stable and has a neutral charge, you have to have the same number of pluses as you do minuses. So if we have 6 protons, we are going to need 6 electrons to make this atom neutral. So now, how do we figure out how many neutrons we need? So look down at the bottom at your atomic mass where it says 12.011. That is your atomic mass, and basically what it is, it's your number of protons plus your number of neutrons. Now, your protons and neutrons are measured in atomic mass units, or AMU, okay? And each has a mass of about 1 AMU. So what we do is we are going to round your atomic mass to the nearest whole number. So you're going to take 12.011 round to 12, all right? And then what we're going to do is we're going to subtract the number of protons from the atomic mass, and that will give us the number of neutrons, because number of protons plus number of neutrons equals atomic mass. So that's not hard to do. We do 12 minus 6, and we're going to get 6. So we know that's the number of neutrons we need. All right, so now we're ready to roll. So you need to go ahead and have a look at this big sheet. By now you should have that little table filled in. And you're going to need to choose a color to represent each subatomic particle. So I've chosen green for my protons, I've chosen red for my neutrons, and I've chosen purple for my electrons. And I have Skittles on hand, so that's what I'm going to use. Now we're going to be using the table you have completed to complete your Bohr model of your atom. So look at this. We're going to put in our nucleus our 6 protons, because they belong in the nucleus. And you know what else goes in the nucleus? Your neutrons. So we're going to put our 6 neutrons right there in the nucleus. Perfect. Now we get to place our electrons. But if you look, you'll see that each of those circles, which represents an energy shell or energy level of the electrons, can only hold a maximum number. So that first one can only hold 2. But the next level can hold 8. Well, we only need to place 6, right? We've started with 2, so we need to place 4 more in the next level. And that gives us 6, and now our atom is complete. You did it. So, ta-da! So why don't we try a different one? Let's give lithium a shot. That's lithium right there, number 3. All right, so we're going to do the same kind of deal. Here goes lithium. We're going to fill in our chart. And now here's where we need to think a minute. We have 3 protons. How many neutrons do we have? Well, we have to round that number, 6.941, up to 7. And we're going to subtract the number of protons, which is 3. So what's that going to give us? 4 neutrons. And then how many electrons in an atom with no charge or neutral charge? 3. So let's go ahead and place them. Here go our 3. Here go our 3 neutrons. Oh, 4 neutrons, sorry. And then here go our 3 electrons. And as you notice, we've got 1 in the second level and 2 in the first level. So we're going to do one more. We're going to give sodium a shot. Here we go. Here's sodium. So sodium, we're going to go ahead and fill that in. That's Na. Sodium, atomic number 11. There's your mass, 22.990. And we have 11 protons. That's our atomic number. There's our neutrons. We got 12. And then this would be because if you're going to round, it's going to be 23. So 23 minus 11 is going to give you 12. And then lastly, we have our number of electrons at 11. And we're going to go ahead and place them. So there they go, 3, 4, 5, 6, 7, 8, 9, 10, 11, and how about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There they go, bouncing in there. And lastly, we're going to go ahead and place our electrons. We got 2, and then plus 8 is going to give us 10, plus 1. There's our 11. So which atoms did you choose to model? So we chose to model carbon, lithium, and sodium. Oops, look, I misspelled sodium. See, in my class, we have this thing called brownie points, where if they catch me before I catch myself making a mistake like that, they get points. And after a certain number of points, they get brownies. And the bummer is that this last week was when they earned the brownies, and a lot of them are absent. So we'll have to do it again later. Does your model accurately represent a real atom? And what can you learn from your model? So my model does not accurately represent a real atom because my model is 2D and an atom is 3D. The parts of an atom are also in motion, and the electrons are revolving around the nucleus in like a cloud, right? Not like an orbit. Even though my model isn't totally accurate, I can still use it to get an idea about how atoms are structured. So our analysis and conclusion is that a Bohr model, while not accurate depiction of an atom, can help you conceptualize basic atomic structure, and that the number of neutrons in an atom can be determined by subtracting the atomic number from the atomic mass. And maybe you have another idea you could put there as your last bullet point. So I need you guys to keep up the good work, practice, 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 And thank you so much for joining Lab Rats Cooperative Learning today.